Welcome back to our Queensland Physics High School syllabus here, where we're looking at classical physics, Unit 3, gravity and electromagnetism, particularly forces on inclined planes. We're going to do a fair few little examples of this and calculations of this, and look at that little puppy, poor thing. All right, think about inclined planes like a street. We know that there are some very, very steep streets around the world. What's often considered that one of the steepest street in the world is over in Dunedin on the South Island of New Zealand. 35% grade, I believe it is. So for every 1 metre it goes up, you're going 2.86 metres across, which is actually a lot steeper than what you think, especially looking at those diagrams there. There's a few other examples. The other one on the right-hand side there is from North Wales, which is almost as steep, but not quite. Steepest street in Brisbane is in Toowong. Not that hard to find, and it's often considered to be one of the steepest in Australia. Alrighty, so where are we up to? We've done our first few there. We're really going to get stuck into these inclined planes, look at how they work, and get ourselves up those first 4 dot points done. So, forces on objects in inclined planes, what we're doing, there will be free body diagrams, we will be working out net forces, and we will be doing calculations. Remember when we spoke about free body diagrams, it's like where we have an object that has a force in this direction, a force in this direction, and maybe some other forces and so on acting to it, and it allows us to work out the net force. So when we're talking about this stuff, what we're talking about is uniformly accelerated motion, because the only form of acceleration comes from gravity. Those are the scenarios we're talking about. And time to talk about dead white guys. Galileo lived a little while ago. So basically, he lived in a time when it was difficult to time things. It was difficult to do the sort of accurate timing of objects like we can do now with stopwatches. So he realised that a way to slow down an object in free fall, that's being forced by gravity, is to basically run it down an inclined plane. An inclined plane is effectively slowing down how an object actually falls. There's still acceleration, but only by a reduced component that it runs along the track that it rolls down, like a ball rolls down, that sort of thing. So, what he's worked out quite some time ago is a little scenario like this. So there's our mass sitting on an inclined plane. We have some angle that the inclined plane is at. We have the weight of the object pulling it down. Now that's causing most of our forces to occur, that weight. We can resolve that into Fg cos theta is this perpendicular force to the inclined plane. It is a force perpendicular to the inclined plane. If this was a flat surface, that would be like its weight. Now, because we have this perpendicular force, the equal and opposite force is the normal force. It's pointing straight up. That is the same thing, Fg cos theta, just the opposite direction. But the one we're interested in is the force parallel to the inclined plane, Fp. Now, this is just the original force sine theta, resolving vectors like we've done before. All right. Now, in this case, we're going to see that the force is mass times acceleration. So there'll be a mg sine theta that goes into that. These are not in the formula book or anything, but as our little study tip says, do yourself a favour and learn them. Just have a pause on that one, see if you can have a go at that one, see if you can work out what's going on there, draw a free body diagram, see how you go. Right, so a bit more vector analysis. We're going to look at 4 scenarios here. We're going to look at an object that is on an inclined plane, like this, and it's going to slide down the plane, which is the first 2 scenarios, both with and without friction. Friction's going to be holding it back. And we're going to look at it being pulled up the inclined plane with and without friction. Okay? Let's hope you get as excited as Vector does there. We do study these examples that don't exist because it helps us give a more simple understanding on what's going on in these scenarios. Righto, number 1, sliding down, no friction. There's our free body diagram there. So we're talking about a smooth surface. We mean it's frictionless, but it's obviously not. And this is our vectors that we had before. We've got our weight. We've got the perpendicular force, which is also the normal force, F cos theta. And we have the parallel force that runs down the slope. So the the force running down the plane is the one that we're really interested in. All right, we're not worried about friction holding us back. The mass in this is really helping us work out the acceleration, as in F equals ma, and that's really all that needs to come into it. So let's look at an example. 15 kilo bag of fertilizer, there's my mass, is allowed to slide down a smooth frictionless incline. I've got an angle here. So we want construct means draw, create a free body diagram. We want to do a calculation of the force parallel to the incline, net force parallel to the incline down the slope. And then we want to calculate the acceleration. Once we know that this, we can work out how it's accelerating down the incline, which will come back to F equals ma again. All right, so first things first, we've written down what we know, and we've got our free body diagram there, which looks exactly like what we did before. What's missing is the frictional force that's holding it back. So that's all pretty straightforward. 2 marks for doing that, easy peasy. Righto, then we want to look at the net force that's running down this thing. Identify, this is part B here, net force parallel to the incline, which is my sine theta there. So that's why it's done there. The mass is 15 because it came from up here. It's g sine theta, so there's my gravity, and angle is 30 because it told me up there. Plug that to my calculator, 73.5 newtons down the incline. It's a vector quantity, so down the incline. Now in part C, calculate the acceleration. So worked out the force going down the incline. F equals ma is going to give me my answer here. That was the force parallel down the incline. That's the mass. There's your last unknown. That should be fairly straightforward. It's an acceleration, 4.9 meters per second squared. Easy as. And you can have a crack at those later. Righto. Now it's the same scenario, but in this case, we've got friction. So we've got this frictional force holding us back. Still got this guy, that's our weight, that's going to cause this parallel force and this normal force, but we're going to subtract that guy from this guy. In this scenario, we've questioned there, what are the possible outcomes if the parallel force is the same as the force of friction? In that case, then the net force, force net equals 0, therefore the acceleration equals 0, therefore the object will remain at a constant velocity. That means it either has some velocity of some number that it's already traveling at, or the velocity will equal 0 meters per second. That's our two options. All right, 34 kilogram child is what we have. There's our mass. Sits on a slippery slide, has an angle of 40 degrees. There's our angle there. We've got a frictional force of 110 newtons holding it back. Determine the acceleration down the incline. So work it out with using our calculations. So think about our incline. There's our child sitting on it. We know that she has a force, he or she, sorry, has a force of its weight, which we can resolve into the force parallel, but there's going to be the force of friction holding it back, which was our 110 newtons. There's the free body diagram. Note the only thing that changed was that. That's now 110 newtons, and the mass component of this is 34. So we can start to work out what is this guy here, and then work out the net force from the two of them. So mg sine theta is my parallel force down the slope. The mass is 34 kilos, told me there. That went in there. G is 9.8, because we all just know that. And 40 degrees is that guy there. 214 newtons is the parallel component of the down the incline. That's not the end of our question though. We know that there is a parallel component and we subtract the friction because they're acting in opposite directions to each other. We have one force going down the incline, one force back up the incline. That's the friction there. That's the parallel force there. So it's the difference between the two. 104 newtons down the incline is the net force. Right, the last part was the acceleration. We come back to F equals ma. We've got a net force now, so that one will go in for there. We have a mass already. A is the last unknown. This is just simple middle school algebra. Plug your numbers in. 3.06 meters per second squared. You started with standard units, newtons. You started with kilograms for the mass, so you will get meters per second squared out. Righto, now we're getting dragged up the incline. So what's changed here is we now have this tension force pulling us up the incline. You still have this gravity. You still have the gravity component that is the force parallel down the incline that causes that. But we have a larger force over this side pulling it up. So towing a car up a hill, a mine cart being pulled up, a cable, that sort of thing, that type of deal. Effectively, the net force has got to be this tension minus the parallel force to give us some overall force to make that go up the hill. Right, example time. Coal cart weighs just over half a tonne. We've got a 25-degree incline. Ignore the friction. We're travelling at a constant speed, so acceleration is going to be zero. Forces are going to be balanced. Calculate the tension in the cable. First things first, free body diagram, which is just like the one I had before. I've got a cable pulling us up the hill. My normal force is there. My parallel forces, perpendicular force is there. My force of gravity is there. The parallel force going down is there. And I have my angle down here. So I want to know the question it asked me, calculate the tension in the cable. So I need to determine this one here to work out what's going on over there. So I need to know my parallel force. Sine theta is the parallel component of the weight falling down the slope. 525 is the mass times G times sine 25, 2,174 newtons. Now I know the net force is constant. That's what I said before. So therefore, the tension and the parallel force must be equal and opposite to each other. So the tension is the same magnitude, just up the slope. So here's where we start to modify outwards machine a lot more, where we're using a pulley and a mass. So it's the same deal like the outwards machine that we spoke about in previous episodes. He's just a dead white guy that came up with a lot of this stuff, interesting stuff. But essentially we have a mass here, which now has this force of gravity here. That force is causing this tension here. Remember, tension is just a force, which is the same as that one there, to pull this thing up the slope. That's the only thing we've changed. Think about, it's theorized that Egyptians may have used this sort of thing to pull a block up a slope using a pulley type arrangement where they've just folded it back on each other. Think about your train lines here where you have a tension in the cable, overhead cable here that runs through the pulleys down to that there. And effectively, you've got your mass here with its weight. The pulleys are amplifying that force, transferring it to the connected here to the wires over there. All right, so what's actually going on here? Where's the stored energy coming from? It's coming from the weight of that object over there. We ignore the mass of the cables, the pulleys, and all that sort of stuff. All right, we can use the Newton's second law to calculate our tension. It's just F equals ma that we've been doing all along. Think about the object of this block, the object of mass 1 on the slope here. If this force over here is bigger, then that's going to be bigger than that one there, and it'll go up the slope. If it's the other way around, the force parallel will be bigger and it will slide down the slope, or they could be balanced and nothing moves. So let's look at those examples. So back to our coal cart, pulled up at a 25 incline. We've got a hanging mass this time of 300 kilograms. So this guy's now 300. This one's still 525. Now you think, well, hang on, 500 is bigger. 525 is bigger than 300, so shouldn't it fall down the slope? No, because that's the mass, that's the weight down there. It's only this parallel component, the sine theta component, that we're interested in, because that's what's going to cause some motion. We sort of see these in this sort of minecart example, which is different from a little engine to pull things out, or horses that we use to pull carts out of mines and so on. Another example, if you've seen over in San Francisco, they have their cable cars, which is underneath the road here in this track is a cable that the trolley bus like clamps onto, and it pulls it up and down the hills. They did this sort of thing in San Francisco because they realized that the wealthy people wanted to live up on top of the hills, but it was hard for their horses to get up and down, so they put in a public transit type system, but the friction between the wheels and the track that over here is not very much, so the cable system there is to help pull the trolley up the hill to control its speed. Righto, what are we going to do in this example? Find the acceleration of the coal cart, find the tension in the cable between mass 1 and mass 2. So in this cable section here. First things first, free body diagram, because it helps us get our thinking right. 300 kilogram mass, 525 kilogram mass. We have our gravity here, we have our sine theta here, and we have our weight of this mass over here. So we're trying to find the acceleration of the coal cart. So we want to start finding our forces. We've got to find this force over here and compare it to this force over here because they're effectively opposing each other. So parallel force is mg sine theta is 2,174 newtons. The weight of the hanging mass, that's this guy over here, mass times gravity, 300 times 9.8, 2,940 newtons. So you can see, despite having less mass, because it's all directed down, it's actually got a larger force. The net force is just the difference between the two. Literally just subtract them. Think of it as the cart here and the hanging mass here, and they're effectively pulling each other. Which one's going to win out? Whichever's biggest. The hanging mass is bigger, so it's going to be bigger. So mass 1 is going to be pulled up the incline, and that's what this here says. How do we find its acceleration? F equals ma. So remember what we said before, the net force is what we just worked out, and the total mass is what's being accelerated. That's mass 1 plus 2, the cart plus the hanging mass. Plug those in your calculator, you've got an acceleration, it's a vector quantity up the incline, 0.928 meters per second squared. The last one is finding the tension in the cable. So the net force of what's going on here is that parallel component pulling us down the slope minus the tension in the cable. As in, here's my cart here, I have a tension in the cable. So the net force of this system is we've got to take out the parallel force pulling us away, and that'll give us the force of tension in that actual cable. So my overall net force is my mass times acceleration, and here's my tension, and here's my parallel component down the slope here. So rearranging all that, force of tension that we really have is this mass times acceleration component of the object plus the parallel component down the slope. It's almost like I'm pulling this object up the slope, so that's a force on the rope, a tension in the rope, and I'm overcoming the weight of it parallel down the slope, so I'm overcoming that one too. So that's why I've got mass times acceleration of the cart, and then that net force that we were talking about before. Put them all together, 2,660. Do yourself a favour, go through a few of these, have a bit of a crack at trying them. Now, on a slightly different tack, data test relationships. We do look at some of these things when we look at our data test. We have good old Newton's second law, which we've resolved for our parallel component down the incline, so mg sine theta. So that is just the g sine theta is the parallel the acceleration component, which is what ended up down here. So acceleration is g sine theta, which we sub into F equals ma to give us that middle formula. This one tells us that force is proportional to sine theta. This one tells us the acceleration is proportional to sine theta as well. That's the sorts of relationships that you'll look at. Think about a graph of force versus sine theta. Should be a linearized graph. We can get the gradient of that one. That tells us everything else that's left in our equation. Now, since that came from over here, mass times gravity is the only thing left. Hence, we can solve for acceleration due to gravity, knowing the mass of the object. We often do these sort of scenarios where we adjust the hanging mass here and we adjust the angle here and keep the thing stationary. So as the angle changes, the component down the incline of this mass of this cart starts to increase. So we've got its mass here, but the parallel component down the incline gets bigger and bigger. So we have to start increasing the mass here to make them sit still, and we can look at the relationship between force and angle to keep it stationary because acceleration is 0. You can have a look at that when you start doing some experimental work. Righto, next one, last one here, dragging up the incline but friction acting. This is the only change right here. It's exactly what we did before. It's all the same forces in the same orientations. We still have everything caused by this bloke over here. It's still acting on those tensions there. So those forces of tension are just exactly the same as each other, and that's what's pulling it up the slope. We still have our parallel component, but we have a friction component to add to that parallel component to overcome with that tension. So a minecart is pulled up a 20-degree incline by a cable attached to a hanging mass. So we've got this time 750 kilos, and we have a frictional force going back down the slope of 1,036 newtons. So we have this force of friction here, which is that guy. Same deal. Free body diagram, calculate the acceleration of the cart and the tension in the cable. It's effectively the same thing we did before. We've just got to add that friction onto the scenario that we're talking about. See if you can have a think about that one before you go on to the next slide. And I'm glad you totally ignored me. Here's our free body diagram, and that's the only change in there, that guy there. So what we need to do is determine the acceleration of what's going on here, and we're using some of the numbers that we've already calculated before. We're saying that the parallel force was the 2514. The force of friction was given in the question. So down the slope is 3550 newtons down the incline. All right, remember, how did I get that number? This number here, mg sine theta is what we did before. All right, calculate the weight of the hanging mass, this guy over here. So it's 383 kilos now, 9.8, so it's 3,700. Instantly you can see which one's bigger. This guy's bigger, so we're going to accelerate up the incline. How do I do my net force? I want to subtract the two forces. So what's going up the incline versus the mass of the weight hanging down. So this one over here, opposite from this one over here. We want to look at these, how these forces here balance this force over here. Subtract the two forces there. 203 newtons is my net force. You can see to do acceleration, that's got to go into F equals ma, just like up here. My net force was 203, but it's accelerating the entire mass of the thing. So that's 750 plus the 383, 0.179 meters per second squared. Tension in the cable is done the same way. So I've got a net force and I've got the tension plus what's down the incline. All right, so the net force is what's pulling me back down versus what's pulling me up. But in this scenario, we do have a frictional force. So when I look at what's down the incline, I have a friction force to add in there as well, which is added in there, gives me a slightly different number. Same deal. Have a look through this example, have a look through the questions at the end, and make sure you know how to do these questions. A little bit of a practical example here about train wheels and friction. If you look here at this close-up shot between a train wheel and the track there, it's very, very little contact patch. That's going to reduce the friction massively. The other thing that's going to help here is the train wheel is made of steel and the track is made of steel, so they're not going to distort very much. When you look at a car tyre, you can see it's a pneumatic tyre. That means it's full of air. The weight of the car is pushing down and it distorts the shape of the tyre ever so slightly at the bottom of the tyre, but it's quite a noticeable amount. When you're going somewhere like onto the sand driving and so on, you want a bigger contact patch with the ground because the ground's so soft and falls apart. So you let your tyres down to get a bigger contact area. But trains don't want to do that. They're a very, very efficient form of transport because they run on a steel track with a steel wheel. Obviously, the weight of the train does distort the wheels slightly, but it's so ever so small that we can't really see it. So, very, very small contact patch that's right there. Very, very low friction, so they work really, really well. Particularly once you get that mass accelerated up to the speed that you want to travel at, the train doesn't need a lot of energy to keep going. The problem with this is, how do you get up steep inclines? How do you stop when in wet weather? If you think about wet weather, then you're going to have water lubricating this gap, this tiny little gap in here, and it's going to be really hard to stop. I know when I was younger, and your parents could probably tell you this, trains would stop at the train station in wet weather, and sometimes they would miss the station and overshoot and have to back up a bit. If you go places that have trams, like particularly Melbourne in winter, when it rains all the time in winter, the tracks are always wet. They want the trams to stop and not overshoot the stations and run people over as they're crossing the street and so on. So trams have like a big tank of sand, and they inject sand into this little gap here to create a bit more grit and friction to help the tram stop in wet weather. And as the track is embedded into a road, there's a little gap sort of in here, and you start to see sand depositing in that little gap in wet weather. As for getting up steep inclines, trains don't go up or down very steep hills at all. If they need to go up a steep incline, they have to do something else, like the cable car I mentioned in San Francisco, or some places around the world, like on the west coast of Tasmania or in places like Switzerland. They actually have like a cog system that the train interacts with, a bit like a roller coaster uses to get up an incline. That's the only way to get up or down steep slopes, but generally train tracks are built with a very low incline to account for this low friction. Rightio, that's us today. We've done a lot about moving up and down inclines, both with and without friction. You really need to practice that stuff. We've done a lot here. Finished off these last two things here, which brings us to our very end, which is time for you to do some practice questions. Don't do a Ralph there. Have a look at some review questions at the end of the exercise. Alrighty, thanks for coming.